Hello everyone, here we'll be discussing 6.2, which is a section on volumes. It's quite an exciting section in my opinion. Basically what we'll be doing is finding the volume of practically any shape so long as we can determine the area, cross-sectional area that is, at any particular point. And the problems we'll be discussing will be able to do that, of course. So let's just recall for a moment volumes of shapes we've seen from geometry. We have seen the shape of the so-called rectangular prism, or otherwise known as box. And if the dimensions are length, width, and height like this, then the volume is just the product of those dimensions. And if we have this shape, the so-called cylinder, which is basically you have a circular base and then just kind of connecting those circular two bases with straight lines all around. And in fact, kind of just imagine a box, but instead of the top and bottom being a rectangle, top and bottom are a circle, and you end up getting this formula, which is pi r squared times h, where h is the height of the cylinder and r is the radius of both of the circles. And then we have this kind of new shape here that we actually probably haven't seen in geometry, but the concept is kind of the same. So what you can call this shape maybe is like some type of blob prism. There's probably better names for this. But a prism really is a shape where you have a polygon shape for the base and for each base, for top and bottom, and then you just connect those with straight lines from the vertices. So imagine like for the rectangular prism, you have a rectangular base, top and bottom, the same rectangle, and then you just connect those with straight lines and you get that shape. For a triangular prism, the base would be triangles. Here, the prism will have a base being the same blob, which is, you may have these weird curves along, but the way we describe the volume here is kind of the same way we describe the volume for these ones, so the idea makes sense, because notice, LW really is just the base area. Here, pi r squared is really just the circular area. And here B represents this base area, B. And h represents the height. So notice it kind of makes sense because all we're really doing is basically adding areas. So this says that LW is this area, and we have h of those areas. So multiply this area by h, that's kind of what volume is defined to be. In fact, if you think of, let's say, like a stack of, or a ream of a sheet of papers, however many papers you have, paper is really thin. So that I think is a pretty good example of that. So you can find the dimensions of each sheet and call that the area, of course. So like let's say 8 by 11 would be 88 square inches, for instance. And then if you have a stack of 1,000 of those, you would multiply, 1,000 by the area, and that would be the volume. The unit there would be kind of weird. In fact, you'd have to find the height, or I guess the width of each sheet, which would be really thin. But of course, if you measured 1,000 of them, measured that height, then that would be a way of calculating the volume. So really, it's kind of a way of saying how many sheets you have. So we're really just stacking up areas in some sense. But again, you think of each area as being infinitesimally thin, or each sheet as being infinitesimally thin, which just means really, really, really thin. So we'll see that idea here. So this is kind of a general case where we have this kind of blob in 3 dimensions, and they're not necessarily connected by straight lines like they are here. It could be weird and curvy throughout. So what we're going to do here, and we're only considering, of course, from the x values A to B. I haven't even drawn a y-axis. Doesn't matter where it is. Imagine it's way over here or somewhere in between. Doesn't matter. So let's pick an x value in between. Okay, and let's consider this so-called plane that cuts through the blob. What we're going to do is we're going to look at a cross-section of this of the blob in this plane. So imagine the shape is something like this. And we'll shade this area. And we can call this area A of x. So this is the cross-sectional area at the point x. So it's A of x. So if we can find the area, if we basically have a formula for the area at each value of x, then we can essentially construct an integral. And the way we do that basically is by cutting this into n many slices, and when you cut this into n many slices, we're basically approximating the volume by these kind of slices. So you'd have one slice like this, another slice like that, but these would be straight slices. So notice it'll be just kind of like, again, it's an approximation of that area, of that volume. So kind of think of what we did with, I'm trying to do this justice. Remember kind of what we did with area under the curve. We approximated by rectangles. Here we're approximating by these blob prisms, so to speak. And one more, let's say, something like that. So I don't know if I'm quite doing it justice, but imagine these are just kind of straight cuts along. Now I made it look curvy like this because that's supposed to be like kind of the inner shape that we get. And I'm kind of trying to do it in a kind of perspective way. But anyways, each of these sections will actually have this kind of area. So again, if you consider, let's say, one of them, let's say you call this point xi and this point xi plus 1, and we'll just use our labeling that we had from Riemann sums. And of course, the width here will be delta x. And then we can say that the volume of each of these, so the volume of each of them corresponding to, let's say, xi, will be the area of xi. Okay, so that's a cross-sectional area. But then since there are straight lines that are connecting those up to xi plus 1, this is multiplied by delta x. Because delta x kind of acts as the height here. So think of this blob prism, but on the side, where the height is delta x. So I think that makes sense. And with that being said, that's just for this one particular one. So that's the volume for this one piece. But if you wanted to find the volume from x0 to xn, where x0, by the way, is just a, and xn is really just your b, then this is really just the sum, the whole volume, there we go, is the sum of these v of x of i's, where I goes from 1 to n. Yeah, I think that makes sense. Now, the way I'm defining it is kind of funny. I guess I'm really defining it by a left endpoint, not by a right endpoint. So it would really start from x0 to n minus 1, but it doesn't really matter how you pick these points. In fact, in reality, you can pick any like x star in between this subinterval, and then you can create a Riemann sum like that. So that's fine, but notice this is just, again, the sum I equals 0 to n minus 1 of a sub xi delta x. Now, this is not actually the volume, this is kind of like an estimation of the volume. But if you take the limit as n goes to infinity of this, then this is exactly the volume. So there should be a limit here as n goes to infinity, kind of written small, sorry about that. But notice this is just a Riemann sum, and we can write this, of course, as the integral from our leftmost endpoint, or rightmost endpoint, a to b, in other words, of the area a of x dx. Very cool. So in other words, the integral of area is the volume, basically. And in fact, this is something that is kind of more intuitive idea, is that when you take derivatives, you kind of lower dimension each time. Kind of think of the power rule, for instance. The derivative of x cubed is 3x squared. Derivative of x squared is 2x. So the power goes down each time. When you integrate, the power gets increased. So we're increasing the dimension when we anti-differentiate, opposed to when we take derivative, we kind of decrease the dimension, so to speak. So one can say that the integral of the area is the volume. That idea makes sense, and we kind of see it here. It's not quite as straightforward as you might believe, but it's there. And you can also kind of say that the derivative of the volume is the area. Now that's a little weird, but that actually kind of has some merit to it as well. We're not going to really be discussing that here, but it's just a good idea to have that intuition. So now we're going to apply this formula with a particular example, and in fact we're going to take a look at some other volumes that you may recall from geometry, and we'll actually prove those. So let's take a look at some of those right now. Right, so for this example, we want to find the volume of a square-based pyramid. So imagine we have this pyramid with height h, let's say, and let's imagine that its base, let's say, has side b for base. Now it's square, so all of these will actually be the same. So it's like a b by h kind of scenario. Now, based on the idea I gave you earlier as far as how we determine the volume, or at least get an integral setup for the volume, it would be best to actually have this on its side, because if we had it like this, and we were to find the cross-sectional image or cross-sectional area, the shape would look kind of weird depending how you have it orientated actually. But instead, if you were to, let's say, center it even at the x-axis, something like this I think is a very good idea. So here, let's imagine that we have this square base like this. No, it looks kind of funny, but this is honestly the best way of doing it, so that we kind of standardize things. Now notice that this is all in 3 dimensions, so imagine that this is the actual endpoint. So that means this would be h, and we're going from 0 to h. H equals 0 to h, x equals 0 to h. I think that makes a lot of sense, because the height, after all, of this is h, we're just putting it on the side here. So now if we take any cross-sectional image of this pyramid, we get this kind of shape right here, where, again, if I were to kind of like draw the inside lines on the other side, you get something like this. So that, I think, does it pretty much justice of what I'm imagining in my head. But now, how do we find the area of each square throughout any particular x value that we pick? So we want to find that cross-sectional area, a of x, for any given x value between 0 and h. Well, in this case, we'll have to kind of see things from its side, but here I just wanted to show you still in 3 dimensions. So if you imagine from the side here, so I'm going to redraw the same thing, but imagine just completely on its side, so we don't actually have that perspective in 3 dimensions. We have this kind of shape here. Now, of course, we need to know the dimensions of this square. So I guess we can call it S, let's say. So it's an S by S square. Now we know this is the base, and the base is B by B. So this is going to be B. And we also know this is H. So really what we can do is we can actually come up with and we know this is X is what we're going up to. So what we can come up with here is basically similar triangles. So notice these are the same, well, they have the same angles because these lines are parallel. We have these interior angles are the same. And then we also have, this one angle is the same for both of them. So we have this small triangle and this larger triangle. So by similar triangles, we get the following ratio. S over X equal to B over H. And since we want to solve for S in terms of X, we can just multiply by X and get that S is equal to B over H times X. Which is good because, again, we want the area of this square in terms of X, and B and H are the given constants, so that's fine. I mean, they're not given in the question, but that's what I call those dimensions of this square-based pyramid. So we're actually golden, believe it or not, because now we can say that the area of X is actually just S squared, because the area is a square with side length S. That's what we're calling it. So notice that's just B squared over H squared times X squared. Now what we need to do is take the integral from 0 to H, those are our limits after all, of this area, B squared over H squared times X squared dx. And we can pull the B squared over H squared out. Perfect. The integral of X squared dx is just 1/3 X squared, or X cubed. This is from 0 to H, sorry. So we get B squared over H squared on the outside. And then inside here we have 1/3 H cubed evaluated between 0 and H. We can pull the 1/3 out. Notice when you plug in 0, it's just 0, so the bottom limit doesn't matter. And then we get H cubed. So in fact, what we actually have here is 1/3 B squared times, well, it would be H cubed, but H cubed over H squared, notice, is just H. So this is actually the area of the square-based pyramid. And this is a result from geometry that we're kind of just given. There is kind of a proof that's given in geometry, and that's that if you were to imagine this point being just kind of floated over to the corner, and then you actually take 3 copies of this pyramid, you can form a rectangular prism. And although that actually works, I think this is a much more convincing argument that it's just 1/3 of the prism area, or prism volume, I should say. Because the prism volume for a square-based prism, remember, is the area of the prism, the area of the base, which in this case is B squared, times h. So here we have 1/3 of that because it's a pyramid. Awesome. So now let's take a look at a few more. All right, so this next example really gets the ball rolling because this will allow us to basically take any shape and rotate it about the x or y axis, and then we can, well, find the volume of that generated solid. So here we'll be doing that to find a sphere. So a sphere, notice, is just kind of like this three-dimensional ball. So there's this kind of like depth to it, you'd imagine, something like that. And there's a center, of course, and the radius. And the radius just connects from the center to any side on the outside of the sphere. So I think that's a pretty good representation of what that is. But now what we're going to do is we're actually going to center this in the xy plane. And what we're going to do is we're going to actually kind of find an equation for the sphere. Well, not really. We're actually going to find the equation of a circle, and then we're going to rotate parts of the circle around the x-axis. Basically what we're going to do, and it's kind of the same idea as we saw with the pyramid, if we pick an x value from, well, notice this is going to be 0 to r in this case. Pick a particular x value and look at the cross-sectional region at this x value. It's just a circle itself. So this would be a of x. The only question is, what is the radius? Because as you can tell, the radius of this circle is this distance up here. And notice that changes as this circle floats from r to negative r, or from negative r to r, whichever way you want to do it. But there is actually a way of finding this height, and it's basically it has to do with the equation of a circle. So let's kind of recall what the equation of a circle is, and it's not difficult to demonstrate what it is. If you pick any point on the circle, let's just say over here for instance, connect them from the center of the circle to the circle itself. The radius is r. The point on the circle will be, let's say, x comma y. So this value will be x, this value will be y. And then by Pythagorean theorem, notice that since this distance is x, this distance is y, and the hypotenuse is r, then we have the following equation satisfied: x squared plus y squared is equal to r squared, and that is exactly the equation of a circle with radius r centered at the origin. Nice. So what that means is that this y value, well, we can actually solve for y here. Now if we solve for y squared, we can subtract x squared to the other side. And then if we square root to get y by itself, we get plus or minus the square root of r squared minus x squared. So this is how we can find y given x. If we want to find the positive one, this would correspond to y equals the positive square root of r squared minus x squared, because it's the same image here, just with this three-dimensional perspective. And here this would be the negative one. Y is equal to the negative square root of r squared minus x squared. But for all intents and purposes, let's just consider only the positive one here. And now we can find this radius, because of course we treat radius as being positive anyways. And we know the actual area of the circle, so we know a of x is going to be what? It has to be pi r squared, and we know the radius in this case is just this distance y, because it's up to the y value of this point. So I think things are good, so it's pi y squared in this case. But we know y squared is exactly this, r squared minus x squared. I think we're doing pretty good here. Now what? Well, now the volume of the sphere is just one integral away from this. And notice we're going from negative r to r. So let's see if this works out. So the volume, of course, according to this will be the integral from negative r to r of these areas. So it's going to be pi times y squared, but y squared ends up being r squared minus x squared. So let me just write that in here. Now there's a lot we can do. Notice we can just pull out pi because it's a constant. So volume is equal to pi outside of the integral from negative r to r of r squared minus x squared dx. Also notice that this is an even function. If you replace x with negative x, you get the same thing. So we can fold this integral in half, which is a concept we saw from 5.5. So this is really the same as 2 pi times the integral from 0 to r of r squared minus x squared dx. Which is something we don't have to do, but it'll just be less work. If you want to do it the other way around, or well, the other way without doing this step, you can. It's just a little more work in the end, you'll see. Now the antiderivative, of course, of r squared is going to be r squared times x, because r is a constant. We're antideriving with respect to x, not r. Antiderivative of x squared will be 1/3 x cubed. And now evaluate this whole thing between 0 and r. Now, when you plug in 0, it's of course 0. And you can see that because everything here that involves x is just a power of x. When you plug 0 into that power, you just get 0 for each term. When you plug in r, here's what happens. We have 2 pi outside of r squared times r will be r cubed. R cubed. There we go. Minus 1/3, well, x is r, so r cubed. And notice 1 minus 1/3, because it's 1 r cubed. So 1 minus 1/3 is 2/3. So we get 2 pi times 2/3 r cubed. And after combining these a little bit, we get the familiar formula for the volume of a sphere. 4/3 pi r cubed. And I think this is really fantastic. I mean, when I learned that result in geometry, I always wondered, why is it 4/3? It seems so arbitrary, it seems so weird. Well, it comes out from integration, basically. And there may be other ways of proving this. In fact, I believe one of the first proofs was essentially by measuring and doing experiments. But once calculus was invented and, I guess, kind of discovered, then this came out, so everything kind of relates back to that. So that's kind of nice. So from here, we're not going to do any more geometry results. Instead, we're going to actually focus on some actual rotation problems. We may do maybe 2 examples, and I think that'll be it for this video. Right, so like I said, the previous problem, the volume of the sphere, gives us this idea of rotation, because we basically picked a point on the circle centered at the origin of radius r, and essentially rotated it about the x-axis. And we're going to see a similar idea here, only we can kind of create our own shapes. So here we want to find the solid generated by rotating the given curves about the indicated lines in between the given values. So for this first one, the curve is y equals x, radical x, from x equals 0 to x equals 1 about the x-axis. I'm just going to try to graph this real quick. The radical x looks something like this, so that's y equals radical x. And we're going from x equals 0 to x equals 1. So its y value is, of course, also 1, because 1 square rooted is just 1. And what we're doing is we're grabbing this curve and rotating it about the x-axis. So imagine doing something like this, like that. So we're just kind of swirling that around, and we're getting this generated solid, which kind of looks like a bullet kind of shape. Yeah, I guess I could do that more justice over here. We have that below and that here, and then we have this part like that. And then the cross-sectional region is just a circle, notice. In fact, that's kind of the main idea, is that since we're rotating, our cross-sectional image will always be a circle. And in fact, the radius of that said circle is just the height at that point x, which notice will just be the function. Because really the height is y, and y is given by this curve, radical x. So really what we want is we want to find, again, the cross-sectional areas, which in this case, much like the previous problem, is pi times y squared, because y is acting as the radius in this case. And also notice y is radical x in this case, so we end up getting this, which of course is just pi times x in this particular case. And now we can of course set up our integral. The volume will just be the integral from 0 to 1, because those are our x values, of the area function, which is pi of x dx. So of course you can pull pi out, but this is so simple we don't even need to do that. This of course is going to be pi over 2 times x squared, evaluated between 0 and 1. And when you plug in 0, it's 0. When you plug in 1, it's just, well, pi over 2. So the actual answer here is just pi over 2. Not too bad. Great. So now for this one, this is a little different because now instead of rotating about the x-axis, we're rotating about the y-axis. And in fact, maybe after this problem, before moving on, I may generalize this idea of rotation. You know, now thinking about it, I may actually have to summarize that after the next example, because the next example will be a more generalization of this idea here. You'll see that when we get there, of course. So now, here we're rotating this curve, which I can graph like this if you like. Y equals x cubed looks something like this. But we're rotating it about the y-axis now from y equals 0, so that's y equals 0 is just the x-axis. So y equals 0 to y equals 8. Maybe this is a better way of describing that. There we go. So from y equals 0 to y equals 8 is where we're cutting off the rotation. So we actually don't really care about this part below. So you can erase that if you like. Didn't mean to make that sound, that's okay. So if you rotate this about the y-axis, you get this shape, which is also kind of like a bullet shape. But it's a lot taller, so it's more like this kind of weird round vase kind of shape is what comes to mind. Or maybe like one of those conga drum kind of things. Anyways, so to actually find this, we kind of have to tilt our heads like we did in one of those problems from 6.1, because this is, of course, well, this has that kind of y feel to it. So if we were to swap the x and y axis, it'll be a little easier to see. But notice the radius of each of these circles will just be the x value. So we can actually find that because we can find x in terms of y. Of course, since we're going from 0 to 8 for y, this will be a y setup. So I want to find the area in terms of y in this case. And it's going to be pi times the radius squared, the radius in this case of each circle. Notice is just x, but you can solve for x by just taking the cube root of both sides. So x is, well, y to the 1/3, let's say. So then combining these, you get pi times y to the 2/3, of course. And I think we're set, because now all we have to do again is just take the integral from y equals 0 to y equals 8 dy. So the volume then is the integral of this area function pi y to the 2/3 between 0 and 8 now. And again, this is a pretty similar problem to the one above, even though it looks a little complicated. Pi is a constant, so we don't need to really worry about it. And since our lower limit's 0, and our antiderivative will just be a power of the variable y, it's actually quite simple. So first antiderivative of y to the 2/3 is y to the 5/3 divided by 5/3, so multiply by 3/5. We still have that pi on the outside, and then evaluate between 0 and 8. When you plug in 0, it's 0. When you plug in 8, let's see. Well, 8 to the 3/5 is, well, remember the 1/3 power means cube root. The cube root of 8 is 2, so then we have 2 to the 5th, which is 32. So when all is said and done, we get 3/5 times pi times 32. And if you bring that up to the numerator, 32 times 3 is 96. So we actually just get 96 over 5 times pi. Or let's write it as 96 pi over 5. That sounds a little better. But it's really the same thing. Awesome. So now again, we'll move on to one more example that will kind of be a broader version of this, and then from there we'll summarize our results. Right, so at first glance this problem is kind of the same, only in reality instead of rotating a curve about a line, we're actually rotating a region bounded by curves. Bounded by, in this case, bounded by y equals x and y equals x squared. And instead of rotating about the x-axis or the y-axis, we're actually rotating about the line y equals 2. Now, of course, the x-axis is the line y equals 0, and the y-axis is the line x equals 0. So there's still lines, of course, but it's not an axis line, so it's a little different. So we have two things that make this different, and I'm going to try to describe what we're doing here, of course, in particular to this problem, and then afterwards I'm going to generalize this idea, and this is a generalization of the previous two problems. So this idea can still actually work with the previous two problems, believe it or not. So also notice we don't have bounds here, so we have to first graph the region and see what's going on. So let's start at that point. So let's see. So we have x-axis, y-axis. X equals, y equals x squared. Let's start off with that. That's this parabola. Perfect. And then y equals x is this straight line like this. And we can see that the region that these two enclose is just this right here. So I'll erase everything else. There we go. So we get just this little region right there. And we can find actually the x values. They end up being 0 and 1. And you can of course find those from what we saw in 6.1. Just set the y's equal to each other, so x squared is equal to x. Of course, if you move things to one side and factor out the x, you get this. If you set each part of the factor equal to 0, you get x is equal to 0 or 1, hence the 0 and 1 here. Fantastic. So now what are we going to do with this region? So let me just shade this region so we know what I'm talking about in red. And we're going to rotate it about the line y equals 2. Now, if you plug 1 in for each of these, you get 1 squared and 1, they're both 1. So the y value here is 1. But we're rotating about the line y equals 2. Now, I probably didn't give this enough height to do the image justice, but the line y equals 2 is, of course, this horizontal line. And if we actually rotate this about this line, the image we get is kind of like this, this hollow shape, kind of like a vase shape kind of a thing. So only it's more of like a sleeve, I guess, because you can fit your hand completely through it. So if we rotate about, the image we'll get is something like this. I'll try to do this justice. We have kind of a small hole here and a larger hole here. It's rounded at the edges, but on the inside it's not rounded. That's a little better. So the inside is not rounded, it's actually straight lines all around. So I'm still not satisfied with that round. There we go, looks a little better. We have these kind of straight lines. And that's of course all around. And then here we have kind of like this circular shape like that. So I hope this kind of does the image justice, but again, if you just imagine rotating this completely about the y-axis, then we'll kind of get that image. So now, well, this is not quite what we expect, because remember that the previous images, the cross-sectional image was just kind of one shape. It was solid, it wasn't hollow like this. So the solid was not hollow, but now we have a hollow shape. So how do we deal with this? Well, let's look at the cross-sectional region, or the cross-sectional area, I should say. So if you pick a point X in between, after rotating, what you end up getting is kind of the shape here. Let me try to draw it. It kind of looks like a circle, but of course there's this empty part to it. So it looks more like a ring. And there's actually a name for this. These are called washers. So I'll draw this washer shape, not in a three-dimensional perspective, but just kind of flat face down after I finish shading it here. And of course there is an inner radius and an outer radius to this washer. So the washer is basically a circle with a circle inside of it. Kind of something like that. Only imagine it's perfect. Doesn't quite look perfect, but it's close. Maybe that's a little better. Yeah, kind of. So now we have these two radii. So we have, let's say, the inner radius, RI, for inner, and outer radius, RO, for outer. Now what you'll notice is that, again, what we're looking at is this shaded region is what we want to find. Now this is actually not too hard to justify. Basically what we're going to be doing is finding the area of the full circle, the whole circle, using RO, minus the area of the inner circle that we're removing with radius RI. And that's not very difficult to do. So let me call this area a W, W for washer. And it's going to be pi RO squared minus pi RI squared. And again, just the outer circle minus the inner circle, and that's this red shaded region. Now what you'll notice is that if you pull pi out, factor pi out, you get the difference of squares of the radii. Awesome. So that's exactly what we're going to be doing here, but notice in this case the radius is from 2. So the first inner radius is up to this point, and then the second outer radius is up to this point, up to this curve. So we kind of have to do some calculation to see what those are. Now, notice here we're going to be using the curve for that y value, and here we're going to be using, well, not the parabola curve, but the line for that second y value. And more importantly, we're concerned with the distance here. So notice the distance here is actually this distance 1, added to a little bit more. And in fact, this way of seeing it, I don't think is the best way of seeing it, but I think this is the best we can do right now. Let's see, how do we justify adding more? So what do you add to get to this y value? So for this y value, this is y equals x. And for this y value, this is y equals x squared. So remember that we're on the curve y equals x and y equals x squared, so the y value for this particular x value is legitimately x for the line and x squared for the parabola. But that's the distance from here to here and from here to here. So that means this complete distance will be, well, I guess maybe 1 isn't actually important. Maybe what's important here really is the complete distance 2. So notice that this distance of the outer radius is actually just 2 minus x squared, because it's the complete distance 2 minus the parabola. I know it's kind of small writing. And then here for the inner radius, it again is the complete distance 2 minus the y distance for the line, which is x. So this is 2 minus x actually. Awesome. So really for any line, it's going to be y minus that, but, or not y minus that, but whatever your y value is equal to minus that. But not entirely though. If it was y equals negative 2, then things would be reversed and we'd actually have to add 2 to that. So you kind of have to be a little careful sometimes. But I think this still works though. So now I think, let me just keep thinking here. Yeah, I think we're okay. So now what we're going to do is we're going to treat these again as our radii. So this is the inner radius, outer radius, and we're good to go. So we have pi times the outer radius squared, which is 2 minus x squared, quantity squared, like that, minus ri squared, so that's the inner radius squared, which is 2 minus x quantity squared, like this. And now for our volume setup, it's just going to literally be, let me erase this here for more space, of course. So now we're set up. Now finally we have the volume is equal to the integral from 0 to 1 of pi times well, this quantity. And in fact, you know what, just to save space, I'm not writing too much or repeating too much. I'm going to actually expand these out. Now when you expand it a binomial, it's the first one squared plus 2 times their product plus the second one squared. So that's going to be 4 minus 4x squared plus x to the 4th minus this, so I need a little more space actually, something like that. And this, of course, is going to be, let me do like this. There we go. This is 4 minus 4x plus x squared. But since we're subtracting, I'll distribute the negative, although once again, not to write too much. So if you distribute this negative, you actually get negative 4 plus 4x minus x squared. Perfect. Awesome. Now can we combine anything? Well, yeah, I guess we can kind of. So notice the 4's actually cancel out completely, and the x squared is combined to negative 5x squared, and that's really about it. So we have the integral still from 0 to 1. Pi we can pull out on the outside. And let's write this, I guess, in order. So the highest power is x to the 4th. The next in line is x squared, which is negative 5x squared. And then we have this positive 4x left. Perfect. So now, antiderivative of each of these terms will be 1/5 x to the 5th minus 5/3 x to the 3rd plus 4 over 2x squared, so it's just 2x squared actually. And you can check by taking derivative, you need to get 4x. Evaluate this between 0 and 1, and then multiply by pi after the fact. Now, since they're all powers of x, plug in a 0, makes it 0. So it's kind of nice that we've been seeing that a lot for these problems, but it's not always the case that you get 0, it just kind of ended up that way for these examples. When you plug in 1, you just get the coefficients added together. So that's pi times, let me border this off a bit. 1/5 minus 5/3 plus 2. And we can combine this into one fraction. Notice that these combine to 3 minus 25. 3 minus 25 is going to be negative 22 over 15. That's negative 22 over 15. And that may sound kind of bad because it's a negative, but notice that 2, this positive 2, you can write as 30 over 15. So that actually saves the day because our answer ends up being a positive value, which is great. It's kind of small though, it's 8 over 15 times pi. Which notice I haven't approximated any of these values, I just basically left them as a multiple of pi, and this I'm going to do no different. But yeah, that represents the area of this solid generated by rotating this region about the line y equals 2. Fantastic. So now, I'm going to do my best to summarize our thoughts on rotation, and you'll see that kind of it's really just the process we've done here. It's going to be a little difficult when you have non-axes lines that you're rotating about, but I'll do my best to describe that, so let's take a look at that right now. So the region bounded by the curves y equals f of x, y equals g of x, and between x equals a and x equals b, about the rotated about the horizontal line y equals y naught, again like we saw in the previous problem, has volume, this guy. So notice it's really just the area of the washers, pi times the quantity, the outer radius minus the inner radius. Now, since we don't know which one's on top, of course we always kind of assume f is on top of g, kind of like what we saw in 6.1. I'm just going to take the absolute value of that to always obtain a positive. And in fact, this idea of taking the absolute value ensures that this is always larger. In fact, basically what this ensures is that we don't have that weird scenario that we had in 6.1, where you have those intersections in between these x values a and b. But anyways, that's kind of detail. And of course they're squared because it's the inner radius squared, outer radius squared, so outer minus inner. But again, since absolute value doesn't really matter which one's which. Integral between a and b of that. So again, the pi got pulled out of the integral because it's constant, and then of course it's dx. Now you may be wondering, why is it f of x minus y naught and g of x minus y naught? Well, as it turns out, that's kind of what we got. We actually got y naught minus f of x, but notice, because we had 2 minus x and 2 minus x squared, if you recall, from the previous example. But notice that if you swap those differences, you get a negative value, but when you square, you get the same result. So imagine like 2 minus 3 is negative 1, but when you square it, you get 1. But instead, 3 minus 2 is positive 1, but when you square it, you still get 1. So the difference inside of a square doesn't really matter, actually. But this is legitimate. Now, you may be wondering, what if you're rotating about a vertical line, not a horizontal line? Well, if we're rotating about rotating a region about a vertical line x equals x naught, we need the following for the region. We need the functions to be in terms of y, so x in a function in terms of y, and we need our lines to be y lines, not x lines. And then we get this, which is exactly the same thing here, only we're literally swapping all x's and y's. And here a and b are y values, opposed to here a and b are x values. Great. And again, what this region kind of looks like here is kind of what we saw from 6.1. We have f on top, g on the bottom. And again, they could possibly intersect. And then between x equals a and x equals b. And if we're doing a rotation about a vertical line instead of a horizontal line, then we have this kind of image on its side where this x-axis is now the y-axis. So this is a region R that we're rotating either about the x-axis or y-axis. Now notice there is a little bit of a problem, and I'm going to leave you a little bit on a cliffhanger somewhat, because the problem, of course, is that that's assuming we can write x in terms of y, which is not always the case. In other words, let's say you had the function, I don't know, how about y equals x squared? So y equals x squared, if you solve for x, you get x is equal to plus or minus the square root of y, which is not a function. And you get this kind of thing going on where it's not one-to-one, basically. So if you were to rotate this about a vertical line, it becomes really hard to write this curve as a function in terms of y. And it's a little hard to see what I mean, but if you were to do an example like that, you kind of understand where I'm coming from, because you almost have to split this up into sections so that our radius doesn't intersect something else. Otherwise, it's really difficult to do. But, as I said, it's a little bit of a cliffhanger because we'll be handling that scenario in 6.3, which is a method entitled cylindrical shells. Now, by the way, the method that we used in this section, as far as rotation goes, is called the discs method. But when you have holes in those discs, like we did for washers, that's the washers method. So these are really the generalizations for volumes obtained by rotating, where you get washers for your for your cross-sectional areas. But again, in that section, I'll be showing you that, that issue a little more, so we'll understand a little more what I'm talking about as far as why it's a problem. And then we'll be kind of looking at a solution, which is much different than rotating. It's kind of rotating, but the way we construct the volume is a little different. And you'll see, it's a lot of fun, like always. So I'll see you in the video for that. Really hope you enjoyed this. See you then.